Hello everyone, welcome to lecture 2 of this lecture series. Last time we were talking about how big numbers, huge numbers or observables are generated by complex systems. In this lecture we would like to set the foundation for investigating in a mathematical way the storyline about these huge numbers generated by complex systems. And let's start with the simplest example. The simplest example would be Brownian motion, or in 1827, the biologist Robert Brown observed that a particle, here we could think of it as the yellow circle, particle embedded or immersed in a liquid, and the molecules would bump and collide with the yellow object and causing the yellow object to move and go through a very jagged motion, which might look like this. So the particle immersed in a liquid might start here, and then it would perform a very jagged motion and would end up at this point after a given time. And so it's like the walk of a drunk person. It has a jagged line. It's like a random walk. And so this is a type of physical example, very fundamental, the simplest, that we would like to put in mathematical language. Now, in mathematical language, an important object to start with is what we call the Brownian motion, symbolized by this B as a function of time, where T here is the time. And this can be understood as a continuous time version of a random walk, or the jagged line that we previously saw in the previous slide. And for any jagged or fluctuations, let's say represented by this coordinate x as a function of time, we could parameterize it as starting from an initial point x sub naught plus this Brownian motion, such that at time t equal to 0, the Brownian motion would also be 0. So at the time t equal to 0, you just have the initial point. The first person who actually studied this Brownian motion was Louis Bachelier, and he was looking at the stock options, and he was of course guided by his thesis advisor André Poincaré, but he was the first one who really mathematically put in mathematical structure this type of random motion, and this was followed by Albert Einstein, of course, in 1905, who later called it the Brownian motion. So the birth of mathematical finance actually started with Professor Louis Bachelier. Now, Brownian motion, we mentioned that at time t equal to 0, it's just equal to 0. If you look at the expectation value or mean of this Brownian motion as it evolves in time, its expectation, we use the symbol E, or as well as this bracket notation for expectation value. Its expectation is actually 0, because in one dimension, for example, it goes to the left, it goes to the right, left and right, and so on and so forth. And if you take the expectation value for a given time interval, then it is just 0. And if you multiply two Brownian motions, let's say this B as a function of time t and Brownian motion B as a function of time s, if you multiply two Brownian motions and get the expectation value of this of the product, then the answer for that expectation value is just the time s, which is the lesser of the two times between t and s, and that's the value of the expectation value of the product of two Brownian motions. So these are just basic properties of the mathematical object which we call the Brownian motion. But in data analytics, we have to talk about another mathematical object which is called the white noise. And we ask ourselves the question, can this white noise or white noise analysis help us uncover the structure of big data, of a given big data? So let's talk about the white noise and define it using the Brownian motion which we have. So now let's try to define this mathematical object which we call white noise, which we symbolize by omega as a function of time. And if you take the derivative of the Brownian motion is the object we encountered previously. If you take its time derivative, then that's simply what we call the white noise or omega. So given this equation, the time derivative of the Brownian motion, which we call the white noise, from this equation, we can get this relation if we multiply the equation at the top, this equation, by dt on the left-hand side and dt on the right-hand side, then you get this derivative of the Brownian motion is just equal to the white noise times dt. Now, you can, of course, integrate also both sides of the equation. And if you integrate both sides of the equation, the left-hand side would just give you the Brownian motion bt, and the right-hand side is the integral of omega s ds, where s here would be time going from 0 to t. So if you have a theory wherein you express all the functionals in terms of Brownian motion, you can rewrite and convert your formalism, your theory, your model in terms of white noise. So in your formulation, if you see a derivative of Brownian motion, you can write that as omega dt. If you see Brownian motion b, you can write that as an integral of the white noise, such that a functional written in terms of the Brownian motion can be converted into a functional in terms of white noise. So if before you see everything in terms of the Brownian motion b, now you can rewrite that so that you see everything in terms of the omega. And we should have a mathematics, a formalism, a calculus to deal with functionals of omega. And the expectation value of omega is, using the same symbol we introduced before for the Brownian motion, is equal to 0. And if you multiply two white noise random variables, omega t and omega s, so t and s are both times, if you multiply them and you take their expectation would give you a Dirac delta function. That means Dirac delta function is always 0. So the right-hand side is always 0 except when time t is equal to s. So it acquires meaning only when t is equal to s. So if there's a difference in time between t and s, then there's no relation between omega t and omega s. They're independent from each other. But when the t and s coincides, that's when it shoots up and there's a spike, which is the delta function. So we now have to think about a framework wherein we can go from finite dimensions to infinite dimensions. We are very familiar with finite dimensions. For example, in your classical mechanics class or quantum mechanics, your independent variable is some xj. J would be x1, x2, x3 for xyz. So instead of xj, we go to, as our independent random variable, we talk about omega t, because omega is, as time progresses, omega is independent from each other, as you have seen in the expectation value of 2 omegas in the previous page. So using this variable in the finite dimensions, you create a coordinate system, a series of x1, x2 up to xn. Here, our coordinate system in infinite dimension would be the omegas, where t progresses, which is a function of the real number. And once you have a coordinate system, you can now define a function defined in this coordinate system. But when you go to infinite dimensions, you talk about a functional. So it will be a functional of phi, a functional of the white noise. So if your previous space was, say, xyz or n dimensions, Cartesian coordinates, then you have a space of Hida distributions in infinite dimensions. And when you do integration in finite dimensions, you normally need the Lebesgue measure. Here, you will be needing to be able to handle functionals of white noise, your Gaussian white noise measure, which we'll define in a little while. So these mathematical objects live in different spaces, where S, for example, is a space of test functions. We will have more of that later, which belongs to the space of square integrable functions, or the Hilbert space, which is also a subset of the space of Hida distributions. So that's how they mathematically define these objects which live in spaces. Now, let's use a notation to be economical in our notation later on. If we have an integral of omega psi, where psi is a test function, and omega lives in the space of Hida distributions. If you have an integral of omega psi, let's denote it by this symbol. And so, for example, if you look at the Brownian motion, which we originally defined as an integral of omega times 1, so if you put psi equal to 1, then this symbol would just look like this. So that's the definition of the Brownian motion, which actually means an integral of omega s. So try to remember that notation, because we'll be using it later on in the succeeding pages. So what is this Gaussian white noise measure, which corresponds to the Lebesgue measure in finite dimensions? The Gaussian white noise measure is defined through its characteristic functional, which means that if you have this Gaussian white noise measure, if you have a Fourier transform or infinite dimensional Fourier transformation like this, and you integrate it, then on the right hand side you have this result. So on the right hand side, there's no white noise variable anymore. It's just the test function psi, in fact integral of psi squared. So one way of defining the Gaussian white noise measure is through this so-called characteristic functional. So the characteristic functional may be written in this way, or it could also be written in this way, the lower equation. The white noise measure, if you look at the mathematical literature, can also be defined or written like in this way. It's infinite dimensional, so you have a d infinity omega. That means d omega 1 times d omega 2 up to d omega infinity. And since this is actually, it diverges, it has to be compensated with a Gaussian fall off. So there you have a minus sign here, so that would be take care of, killing off the divergences that might happen, coupled with a normalization. So anyway, this is how one could look at the Gaussian white noise measure, but most useful would be the characteristic functional later on. Now with that, with this definition, we can now define T transform. We were used to Laplace transform or Fourier transform in finite dimensions. Here we have we can define a T transform. Suppose you start with a functional phi omega, this phi omega. Then you can transform that, and you can define the T transform of phi omega by this infinite dimensional Fourier transform, multiplying it with this exponential, and then integrating with respect to the Gaussian white noise measure. So if you have functionals of omega, the only way you can handle this, or do some integration, or do some mathematical manipulation, is you have to make use of this Gaussian white noise measure. There's also what they call the S transform, and the S transform is defined. You can get the S transform of a white noise functional if, suppose, you already have the T transform of the white noise functional phi, then you just put minus I in its argument, multiply with the characteristic functional, and then that would be your S transform for that particular white noise functional. This is also a relation between the T transform and the S transform, again linked by this characteristic functional C psi. And we can use these definitions and have small exercises, little exercises, just so you can dive into this type of notation, dive in into this type of mathematics. So this is the end of lecture 2. And of course, I can discuss with you privately some exercises. Thank you very much. And I'll see you in the third lecture.